Okay, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have been talking about the known as well as the unknown quantities. So, these were the unknown quantities. Unknown quantities V theta, V internal, theta internal, and we have also noted down the particular dimension, and accordingly we have also noted down the actual dimension of this unknown vector. So, we can say that this is nothing but unknown vector So, unknown vector x has got a dimension 6n plus 2m minus 1, where n is the number of bus and m is the number of generators. And v theta, v internal, theta internal we have already discussed. Similarly, the known vector m constitutes of 4 different subvectors: p specified, q specified, p generation, as well as the v specified. Now, we have not discussed about their dimension. Now, p specified would be, please note that p specified is nothing but the specified power at each of these original n bus corresponding to each phase. So, then therefore, if my number of bus is n, so then therefore, number of p specified quantities would be 3n. So, then therefore, it will have a dimension of 3n cross 1. Similarly, q specified also is nothing but the specified reactive power injection at each of this original bus corresponding to each phase. So, then therefore, for n bus original system, please note when we have got n bus system having m generators, actually the size of the augmented system becomes n plus m bus, but then p specified and q specified are actually the quantities associated with the original n buses. So, then therefore, q specified would also be 3n cross 1. P generator, now apart from the slack bus, or rather apart from the slack generator, we would be able to specify the total generation for each of the remaining m minus 1 generator. So, then therefore, its dimension would be m minus 1 cross 1, and V specified is nothing but the specified voltage magnitude which should be controlled by the excitation system at the terminal of each of these m generators. So, then therefore, this dimension would be m cross 1. So, then therefore, total again becomes 6n plus 2m minus 1, correct. So, then therefore, number of unknown quantities is equal to the number of known quantities. So, then therefore, this system is now solvable. Now, before we start solving this set of equations, let us do some recapitulation of the balanced load flow. So, recapitulation, which we will basically try to recollect that what we actually do in the case of balanced load flow, and then we will straight away import that method in this case also. So, recapitulation of NRLF polar technique for balanced system. So, we will simply do the recapitulation, and using those we would be using that concept we will straight away solve our equations. So, now what happens in the case of a balanced system? We have two actually known vectors, P specified and Q specified. And again we assume that there are n bus system. We assume that there are n bus M generator system. So I mean, before I talk about the known vectors, let us first talk about the unknown vectors. And here the assumption is that the generators are connected at first m buses. So assumptions are the generators are connected at first m buses and bus 1 is the slack bus. Slack bus. So then therefore with these assumptions our unknown vectors becomes theta first, theta, and that is basically theta 2, theta 3 dot 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 theta n transpose t. So this dimension is n minus 1 cross 1, and v, that is the v magnitude, and we are also assuming that the now because this generators are connected at first m buses, so then therefore first m buses are considered as a PV bus, so then therefore the voltage magnitudes at those buses are controlled by the generators. So then therefore you have to only solve for the load buses. So then therefore, so here the V vector would be Vm plus 1, Vm plus 2 dot 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 Vn t. So it is basically n minus m cross 1. So here essentially we denote that theta is the voltage angle at bus I, and Vi is voltage magnitude at bus I. So I mean this is the notation here. So obviously in this case I basically varies from 2 to n. So here in this case I basically varies from 2 to n as I can see, and in this case I basically varies from m plus 1 to n as I can see here from here. So then therefore my unknown vector is theta v, theta v, and its dimension is 2n minus m minus 1 cross 1. So I mean these are the unknown quantities. What are the known quantities? P specified. So P specified means we now at all the load buses the injected powers are known, and all the PV buses also the injected powers are known because the generator powers are known except the slack bus. So then P specified is a vector, it is also a vector, it is P2, P3 dot 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 Pn transpose, and Q specified is only for the load buses because for the generators we do not know, but for the load buses because the loads are known, so then therefore the specified reactive power is nothing but the negative of those. So then therefore we know that Qm plus 1, Qm plus 2 dot 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 q and t. Again this is n minus 1 cross 1 and this is n minus n cross 1, and the definition is that P2 Pi is here that injected real power at bus I. Of course, here again I is equal to 2 to n, and Qi is nothing but injected reactive power at bus I is equal to m plus 1 to n. So these are the known vectors, these are the unknown vectors. So then therefore using these known vectors we define an vector m and we say that it is pq. And this is has got dimension 2n minus n minus 1 cross 1. So for a balanced system this is the known quantities and the unknown quantities. Now how do I solve? We solve it, and then after we do all kind of linearization and all that stuff, and then ultimately what do I get? I get the equation after linearization and etc. Linearization we get, we are not repeating it because we have already done it in an earlier course. We get that the delta p, we get actually this delta q, delta p delta q is equal to, we say that this is the Jacobian matrix J1, J2, J3, J4, and this is delta theta, delta V. So we know all this, so everything is known, and because, and then of course this J1 will have an J1 will have the dimension is n minus 1 cross n minus 1, and J2 will have dimension n minus 1 cross n minus m. J3 would be dimension will have n minus m cross n minus 1, and J4 would be n minus m cross n minus m. And this is very easy to interpret, or rather remember to interpret, that this is n minus 1 cross 1, this is n minus m cross 1, and this is n minus 1 cross 1, this is n minus m cross 1. So then obviously this, now this J1 connects del p with del theta, so then therefore this J1 will have to be n minus 1 cross n minus 1. J2 connects del p with del v, so then it has to be n minus 1 cross n minus m, and so on and so forth. And what is actually J1? J1 is actually, we know that J1 is actually del p by del theta. I mean this is the vector. J2 is del p by del V. J3 is del Q by del theta, and J4 is del Q by del V. Right. So now obviously now basically, although here we have written del P by del T, but then this is a matrix, as we have seen that J1 is a matrix which is a square matrix, n minus 1 cross n minus 1. So what are the elements of J1? So J1 elements are basically del P2 by del theta 2, del P2 by del theta 3, then dot 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 del P2 by del theta n, and then del P3 by del theta 2, and then del P3 by del theta 3 dot 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 del P3 by del theta n, and then so on and so forth, and then lastly last is del Pn by del theta 2, del Pn by del theta 3, and the last element is del Pn by del theta n. So this is J1, we already know that. What would be J2? J2 would be J2 is del P by del V. So it is basically del P2 by del Vm plus 1, then del P2 by del Vm plus 2, then dot 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 del P2 by del Vn, and then it is del P3 by etc., and then dot 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 del Pn by del Vm plus 1, then dot 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 del Pn by del Vm plus 2, dot 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 del Pn by del Vn. Right. So basically partial derivatives of all p's with respect to all voltage unknown voltages, and so on and so forth. Similarly, J3 and J4 also can be defined. So we have J3 is del Q by del theta. So it is nothing but del Qm plus 1 by del theta 2, then del Qm plus 1 by del theta 3, and then dot 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 del Qm plus 1 by del theta n, and then it goes like this. So the next row would be del Qm plus 2 by del theta 2 n, and so on and so forth, and then lastly last row would be del Qn by del theta 2, then del Qn by del theta 3, and then dot 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 Qn by del theta n, and J4 is del Q by del V is equal to del Qm plus 1 by del Vm plus 1, and then dot 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 del Qm plus 1 by del Vn, and then so on and so forth, del Qn by del Vm plus 1, and then it will go like this, del Qn by del Vn. So J1 and J4 are square matrix, and J2, J3 are rectangular matrix, and the individual elements are this. And essentially we know the expressions of P and Q, that is we know the expressions of Pi and Qi, which are expressible in terms of theta and V, that is basically theta and Vi, and using those expressions we do calculate their partial derivatives, and then we proceed, so on and so forth. So going by this same, similarly, now here, so similarly, because here known quantities is at the left hand side and the unknown quantities are at the right hand side, and then here they are, so then therefore by same token we can write down that my known quantities are del P, del Q, del P gen, del VSP. So I can say similarly for three phase system, I can say that by the same token del P, del Q, del P gen and del V specified, that is the known quantity. So this is nothing but the del M vector, this would be nothing but the del M vector, and there would be some Jacobian matrix, and here also we have the unknown quantities, and the unknown quantities in our case is say del theta, del V, del theta int, del V int, right. So let us write that here. I mean, we are just changing the order a little bit. So let's say del theta, del V, then del theta internal, and del V internal, correct. And so now I have got, now in the case of single phase I have got two subvectors in the known vector and two subvectors in the unknown vector. So then therefore total number of submatrices in the Jacobian matrix is 4, 2 into 2, J1, J2, J3, J4. In the case of three phase, what I have got 4 subvectors in the known vector and I have got 4 subvectors in the unknown vector. So then therefore by following this same logic, the number of submatrices in the Jacobian matrix should be 16, right. I mean it would be 16 because 4 into 4. So then therefore it would be J1, we will just write it, and then J1, J2, J3, J4, J5, J6, J7, J8, J9, J10, J11, J12, J13, J14, J15, J16. So what I have got? I have got 4 submatrices. I've got 4, or rather 4 known subvectors, 4 unknown subvectors, and connecting them I have got 16 submatrices of the Jacobian matrix. So this is then therefore in the so this vector is delta m. This vector I can say that this is delta x vector, and this big matrix is my big, very big J matrix. Correct. Now what are the definitions and what are the dimensions and etc etc. So now it will, so then for our 3-phase load flow analysis we have to find out the elements of each of these submatrices, or rather we have to find out the expressions of the elements of this each of these submatrices, as well as their dimension. So we will start this topic from the next lecture. Thank you.